Okay, we're going to use a program called MolView. The website is at molview.org to visualize some molecules in 3 dimensions. This is going to help us figure out kind of the 3-dimensional shape of how atoms are arranged each other and near each other when we make covalent bonds. We also have these physical models we call snatoms in class because they're atoms that snap together. But we are just going to focus on kind of the MolView part of this in this video. So what we can do with MolView is look up chemicals by a common name, like acetic acid, or we can look them up by a technical name, like we will see. Let me see if I can find a good. Well, I'll look at it like this. Like our hydrogen peroxide here is going to be H2O2. It's gonna be kind of messy. I'm doing this with a mouse. So we could look it up by the formula, or we could turn that into a technical name like dihydrogen dioxide, something like that, and then go from there. MolView will generate an image and a structure for that molecule as best as it can. It has a huge database of information that it draws from, so a lot of stuff you can find pretty easily. Sometimes you might have to try doing a formula instead of a name or vice versa, but you can usually find it pretty easily. Okay, so let's try checking out MolView. Switch to this. Okay, so you'll be greeted with this screen here. It's just, asking for donations and things like that. We can just close that for now. Okay, we're greeted with a molecule of caffeine. So on the left side, this is color-coded to match the atoms over on the right. I can click and drag and rotate this and spin it around so I can see this in 3 dimensions. Okay, I can see how these white atoms right here, these hydrogen atoms, are kind of sticking out in different spots, which is kind of cool. So it's not all just flat like it's drawn over here. Okay, I can also zoom in on it. If I want to get a better picture of it, I can zoom out if it's a really big molecule, and things like that. Now, at the moment, this seems to be missing some things. Like, I don't know what all these sticks are that just kind of come to like a sort of like a triangle here, and then like this just kind of goes off in the distance. What is this stick here? Well, when we have very big molecules, we sometimes hide carbons and hydrogens because they end up being the skeleton of very, very big structures. So to simplify them, we just kind of hide carbons in as kind of the points on these lines, like the end here or here or here. And we assume that if we don't show that carbon being bonded to other stuff, it is as full of as many hydrogens as we can fit it, as many as we can bond it with. So to explicitly show those, we just use this little CH button up here. And that shows everything. It shows all our carbons, all our hydrogens, and they're still kind of color-coded to match what we see over here. Now, I might have to kind of rotate it a little bit, but it's mostly in the right spot. Okay, if we want to see other molecules besides caffeine, they've kind of shown us here, we can go up to the search bar and type in whatever we want. So I could type in water and get the molecule of water to be shown here, my 3D structure here. I can spin it around, I can zoom in, zoom out. Okay, and again, I've got the structure drawn over here. This is the Lewis structure. It's not showing the valence electrons, the extra dots that would be on oxygen that aren't being used for bonding, but it gives us the general idea, and that's good enough for us for now. Okay, the first molecule we're going to look at is called acetic acid. So I'm going to type in acetic acid. All right, and I get something like this. So this is my 3D structure of the molecule. This is acetic acid, okay, commonly known as vinegar in dilute concentrations. You can just go pick up at the store. Okay, and this is how it looks kind of drawn out. So this structure on the left is what I'm going to draw on my assignment, okay, on our lab. And this 3D structure is going to be similar to what we could build with our snatoms. Okay, it's going to be similar to kind of the model that we can make. So since we're focusing kind of on the drawing the Lewis structures aspect and stuff like that, and the naming and writing formulas in this video, switch over to this, and I'm going to be drawing in here what I saw on the other page. Now, you don't have to do all the fancy color coding because that would take a while. So we're just going to kind of cut to the chase. So let's see if I can remember this. So we have a hydrogen bonded to a carbon. And that carbon also has another hydrogen here. Another hydrogen here. So it's bonded to 3 hydrogen atoms. Then it's also bonded to another carbon atom. All right, which I believe is bonded to an oxygen atom with a double covalent bond. Let's see if I got that right. Yes. Okay. We've also got this carbon bonded to an oxygen atom here, which is then bonded to a hydrogen atom. Okay, and again, we're not showing all the valence electrons, but we can figure kind of and double check our octets here. So carbon should start with 4 valence electrons, 1 there, 1 there, 1 there, and 1 there. And by making 4 bonds, it has now gotten up to having co-ownership over 8 valence electrons, which is good. This carbon over here has also made 1, 2, 3, 4 bonds. So it's got its octet. Each oxygen should be making 2 bonds, okay, because it starts with 6 valence electrons. So if I wanted to, I could show in these other valence electrons that would be on that oxygen. Again, for today, we don't have to really worry about the valence electrons too much, but it's good practice to show all of them. So to make sure that our oxygens aren't coming up short, they should have 1, 2, 3, 4 valence electrons not being used in bonds, 5, 6 being used on their side of the covalent bond, and then having co-ownership over 7, 8 on the other sides. So either to this carbon or to here to here. Okay, so this is my structure for acetic acid. And now this picture that I have, this drawing, this Lewis structure, is not a perfect rendition because it is flat. It doesn't show that these hydrogens are moving, kind of into the screen and out of the screen in a sense. But it gives us a decent idea of what holds this all together. Okay, now if the word acetic looks a little bit familiar, okay, that is because we have a polyatomic ion that actually makes up quite a bit of this structure. Okay, the polyatomic ion, let's see, this might be a little too big, but we can try it. Acetate makes up a big chunk of this. It's C2H3O2. Or you could write it as CH3CO. In whichever case you use, it's got a negative charge. Okay, well, looking at this CH3COO version, you might be able to see it better. We've got CH3 here on the left, and then this is COO. So this part in here is actually our acetate. Okay, it's got the same formula as that polyatomic ion. What makes it acetic acid, this acid part right here, oh, I meant to change to red, makes it acetic acid is this extra H we've thrown on there. Okay, so for the formula, you could write this a couple ways. You could just say, I'm just going to count up everything. And so I'm going to have C2, a total of 1, 2, 3, 4 hydrogens, H4. And then 1, 2 oxygens, so O2. Okay, or you could say, hey, this is basically the acetate polyatomic ion with hydrogen in there too. This is also a great example to show that polyatomic ions are held together with covalent bonds. They are a group of atoms that have a charge overall, but that group of atoms that have a charge is actually a covalent molecule. So if you wanted, you could also rewrite this as H first, hydrogen, just a hydrogen that's on the end there, and then C2H3O2. So instead of it kind of doing a give and take of electrons in this case, we've got our acetate polyatomic kind of group of atoms covalently bonded to a hydrogen atom, which is kind of neat. Okay, a lot of times when we see this, kind of bound up with like a metal, this would make a nice ionic compound with something else, like sodium acetate or potassium acetate. But we can actually make covalent molecules out of this too by doing one of these kind of bonds. Okay, now the rest of the examples we're going to go over are going to be a lot easier. I like to do this one first because it is kind of a toughie, and it's kind of a lot going on at once. We got a polyatomic ion, we got a big structure to draw, and we got a formula and all that jazz. So let's try some easier ones. We'll go to hydrogen peroxide next. Okay, both of these are common kind of cleaning agents or disinfectants that you've probably seen kind of used around your house. Hydrogen peroxide is not that good of a disinfectant nowadays, since we know that it actually can kill some good skin cells alongside killing kind of the bad bacteria you're trying to get to. But anyway, it's kind of outside the purview of this video. Let's look up hydrogen peroxide on MolView. So I'm just going to type in hydrogen peroxide. See what we get. Ooh. Okay. So I got something interesting. This looks a little odd. Okay, and this is one of the things that I kind of mentioned you got to kind of watch out for. MolView does its best to search its database to try and find something for you, and this over on the left looks good. This on the right, not so much. So for now, this will be okay to help us kind of draw our structure, but we might come back and try and find a different kind of version of hydrogen peroxide that we could use to build a model that more represents this. So for now, we've got an H bonded to an O, bonded to an O, bonded to an H. So let's draw that in here. Got an H, got an O, got an O, and got an H. I don't think I drew that exactly like what MolView showed me. Okay, yeah, there's kind of dipping down first, and mine kind of goes up first, but that's okay. It doesn't have to be exactly the same. It is showing the same kind of general structure of the bonds, and that's kind of what's most important here. Okay, so there's actually a polyatomic ion kind of that's found its way into this one as well. Peroxide, let's write over here. Peroxide, actually O2 with a -2 charge, okay, which is what's happening here. Except again, in this case, this isn't making an ionic compound, we're using it in a molecule. So it shows up, and instead of doing a little give and take to take electrons from something else, like again, sodium or potassium to make sodium peroxide or potassium peroxide, instead we are making covalent bonds with hydrogen. Okay, which is where we get this name, hydrogen peroxide. Okay, so if we wanted to name this, aside from just calling it hydrogen peroxide, okay, I can note that my formula is H2O2, okay, 2 H's, 2 O's. And you might say, oh, well, I want to do 2 O's and then 2 H's. That's fine. I would count either one. But this is kind of the more common way we see it with the H's first. It can be kind of something you have to get used to the more you do examples. You kind of get an idea of like, ooh, this one goes first or this one goes second. So I would take either one, but for this example, I'm going to write it as hydrogen first and then oxygen second. And actually, here, let me. So H2O2 is going to become di for 2 hydrogens, and then hydrogen, dihydrogen, and then my oxygen, I always have 2 of those atoms, so di for 2 again, dioxide. Oxygen becomes oxide as the second element. If you wanted to do it the other way around, you could do dioxygen dihydride, and that would be fine too. Okay? Now, just to see if we can get a better picture of the hydrogen peroxide in 3D, I'm going to go hop back to mole view. Let's try just typing in H2O2 and see what we get. Ooh. Oh, that's much better. Yes, that is our H2O2 molecule. That's our hydrogen peroxide. Now, just for kicks and giggles, I don't know if this one will work, but let's try it. Let's try dihydrogen dioxide. Ooh, it's even shown up in the list there. I'm going to click it and see what happens. Hey, and it reloaded the same one. So that's a good sign that our name is correct. Okay, otherwise, if it was wrong, it would have given us a little error message of like, oh, this isn't something you can look up. So, this can recognize it as, this is hydrogen peroxide, or also called dihydrogen dioxide. So it should mean that our name is correct, which is nice. Check that one off. Okay, so if we go down to some other examples, like acetylene and dioxygen, these are both something that are important as a fuel mixture in welding for getting very hot flames. Okay, out of your torch. Okay, so I could again go look up what acetylene is and go look up what dioxygen is on MolView. So let's do that. Let's do acetylene. Acetylene. Ooh, there it is. Okay, so I've got two carbon atoms with a triple bond in between, and each of those carbon atoms also has a bond to hydrogen. So a pretty simple molecule, which is nice. And again, in the MolView look of it, it's got kind of a slant to it, but if you rotate it around, it looks the same. So I'm just going to do it straight across. A little bit easier to draw that way. So there's my acetylene. I've got my Lewis structure there, and I could make a physical model if I was in class with the SNATOMs. Okay, let's see. My formula and my name come next, or at least the chemicals formula and name. So for the formula and for the name, I'm going to do carbon first, then hydrogen. I'm going to try and leave hints like this when I can, so that way we can kind of get practice with the common way that you would see the formula or name. So that way you get some kind of practice with that. But again, I wouldn't count it technically wrong if you did hydrogen first and then carbon. It would still depict the same atoms. It would still have the same composition. So anyway, so for our formula, we're just saying how many C's and H's are in here. We're starting with carbon. So I'm going to do C, a little 2 to say there's 2 carbons, and then H. There's 2 hydrogens here, so it's going to be H2. All right. The name of this just takes the formula and puts it in words. Okay. If you need the prefixes, they're on the last page, all the way down past all this. You've got kind of a reminder on drawing covalent bonds and things like that. And then naming covalent bonds, we got the rules down here and the prefixes down even farther. So let's head on back. Okay, so we might call this acetylene kind of as a common name, but if we wanted a technical name for this, this would be di for 2, dicarbon. Dicarbon. Di 2 hydride. Hydride. Okay. And again, I don't have to do this, but I'm going to go check back on MolView for funsies and see if this works. So if I type in C2H2, let's see if MolView can figure out what it's supposed to look like. Okay, came up with the same thing. Good sign. Let's try dicarbon dihydride. What's thinking? Let's see. Nope. Well, that's okay. We got the formula to work, and that's still a good sign we're on the right track. So not everything, again, is going to be in the database. And again, sometimes you type it in, you might get a couple examples that you can try and pick out of the list that are for sure in there somewhere and might be what you're looking for. But that will suffice for us. Okay, let's do one more. We're going to look at dioxygen. Dioxygen. Ooh, nice and simple. Just 2 atoms of oxygen bonded together. This will be a nice quick one to end the video. O, double bond O. And again, we're not showing valence electrons. If we did, let's see, oxygen should start with 6, Right now, each oxygen is shown with 1, 2 valence electrons on each end of the bond. So 1, 2, 3, 4, 5, 6 valence electrons, kind of over there. And then this one also would need a total of 1, 2, 3, 4, and then it's 5, 6 that are in this bond here. Okay, my formula just involves oxygen, so all I would need is O, and then 2. And this version of oxygen is actually the kind that we use to breathe. It's about 21 to 22% of our atmosphere, depending on where you measure it, and it's vital to our survival. It's also the kind of natural way we find oxygen out and about. We usually don't find oxygen as a single atom floating around. We find it as this diatomic molecule because this is more stable than just having single atoms of oxygen floating around. Okay, so for the rest of these, you'll just be looking these up on MolView and then figuring out the formula and the name, or one or the other. In some cases, just the formula, sometimes just the name, sometimes both. And again, there's little hints to tell you kind of which one will go first, so they're easier to kind of get an answer that you can plug back into MolView and see if it works on some of them. Okay, and we're just drawing kind of the general structure that you see on the left side of MolView. The right side 3D model is something you can kind of spin around for fun and see, what the molecule would look like, kind of three-dimensionally, and it's basically how it would look if we could make a physical model out of it. But for what we're putting down on paper, we're just going to focus on drawing out the Lewis structures.